Well, good morning, sir. I'm Professor Satrajit of Computer Science Department. So, Shidato sir is also here. Shidato sir?
Yes, yes, I am present. I am present.
Okay. So, you please introduce sir to our students. Already he has been introduced many times. So, but still, please introduce him, and we will start the session within 2 minutes. Okay. And already I have start recording. Okay. So I will upload it in the YouTube on Tuesday when I go to the college. So and I will provide the link to you, sir. So you can download it, and as per Siddhartha sir told that you need that, so you can download it from that YouTube. So that is not issue. So I'm start recording it, the session, intersession. So you are not audible.
Okay, okay. So good morning, everyone. Today our discussion topic is infix, postfix, and prefix expression and their interconversion. Okay. Today our speaker name is Dr. Pritam Bhattacharya from BITS Pilani, Goa. He is an assistant professor of BITS Pilani, Goa, Department of CSIS. He have completed his PhD from IIT Kharagpur, and now his current research topic is uh, approximation algorithm on art gallery problem. Okay, so I would like to now I would like to welcome Dr. Pritam Bhattacharya to deliver his talk. Over to you, Pritam. Over to you.
Okay, thank you, Siddhartha, for the nice introduction. So, yeah, so today my topic is, as he mentioned, basically I'll be using this data structure called stacks to show an interconversion between certain ways of representing arithmetic expressions. So, just to confirm, is my whiteboard visible to all of you? I have shared a whiteboard. Right?
Yes, sir. Yes, sir, it is visible.
Okay. So, okay, so there are two things. First, let me give a very brief introduction to what is this data structure called stack. Okay, so okay, so imagine a situation where you are uh, station. Okay, so typically what happens is, right, now the people will be joining one after another. That is, let's say here one person joins and another person joins. Here the third person, fourth person. Now notice one thing. Uh, they are always going to join the line from the end. That is from like this side. That is the opposite side of the ticket counter. So this is my ticket window, let's say. Okay. But on the other hand, when like one person gets to buy his ticket, he will be leaving the queue from the other side. That is, when we are talking of people exiting the queue, it's from this end, right? So this similar idea, I mean, this idea of how queues work in any kind of service center, whether it's a ticketing counter or say buying tickets for the movie, whatever. So using this same idea, there is one data structure known as queue, which is basically just the same idea. Uh, so queue is basically known as a FIFO. What data structure? What do I mean by FIFO? Means first in and first out. So that is what's happening, right? I mean, yeah. Sorry, someone had a question. Yeah. So you can see that the person who joins the queue at the beginning hit first, right? Whereas the person buys right at the end, he will have to wait his turn, and like he will also get his ticket at the end. So So that's why Q is known as a first in, first out data structure. So, I mean, it's a very intuitive kind of structure because, I mean, we actually see queues a lot in real life, any ticketing counter and all. Right. Now, now just to compare the data structure that I'll be mostly talking about today, that is called a stack. Now, in contrast to queues, stack is known as a LIFO structure. What does that mean? The last in, first out. So basically, try to this say this sort of bucket is a stack. Now, uh, so so this side is called like the bottom of the stack. So let me sort of demarcate the. Okay, so now what happens is in this case, why it's last in first out? So basically, whenever something has to enter the stack, it will enter from the top side. Okay, but when someone has to leave the stack, he also has to leave from the top side only. So what happens is actually, and until the top person has actually left, there is no way for the person below to leave. He is like trapped in. You can think of it in that way. So the until the person on top actually leaves the stack, the other people at the bottom are not able to leave. Okay, so you cannot leave from the bottom. Like this side, it's like a it's like which is sort of open at both ends. So from one way you only get to enter, from the other way you get to leave. Here, the only from the top side of the stack you are allowed to enter, but you also have to leave from there. So here, what happens is this last in first to leave. Okay. Now, of course, this does not work very well for scenarios like a ticketing window and all. Of course, it's a very unfair thing, but it has its advantages. So let's discuss some very interesting problems. I mean, I'll ultimately prefix, postfix, and how they can be. But before that, let's build some intuition how data structures work. So, by the way, there are a couple of terms. This as intuition is known as a. And when an element leaves the stack, this operation is known as pop. So just keep these things in the course of our discussion. Right. So when I say push an element X into the stack, it means you add it to the top of the stack. And when I say pop from the stack, it means you just take it, you just remove it from the top of the stack. So now, like the new top of stack will be the element which was previously just below it. Okay. Yeah, so I think it will become even more clear as we see examples. Okay, so let's consider one problem. So I believe all of you are familiar with writing C programs, right? At least. Uh, Now in C programs, you have seen that, let's say you can have nested loops or nested if then else, right? So let's say if you have a nested loop, for example, if you have like for some I equal to 0, I less than 9, I plus plus. So usually after for you put the body within these braces, right? And then let's say you have a nested loop for j equal to 0, j less than 9, j plus plus, and again you have the body for the nested loop. And then you may also have like a separate for loop at the end of this on some other variable. Let's say for k equal to 0, k less than 8, k plus plus, and again you have a body for this loop. Now notice that if you look at the order in which these braces appear, right, when you have this sort of a nested loop, you have like opening brace, then closing brace, right? Like, and then you have the opening brace and the closing brace for this second loop. I mean, in general, you are not going to ever have a scenario where you start with like a closing one and then have an open one. That makes no sense, right? Because you have to first enter the block, so you need to have the opening brace first, only then the closing brace. Also, you cannot have to like, I mean, you cannot have a scenario like this. That is, you had one opening brace to begin with, then there was one closing brace, and then you get another closing brace. So this closing brace is not matched to anything. I mean, compare it to this situation. So let me just highlight. So here, like this, here also we had two consecutive closing braces following one another, but for this closing brace, you could say that it was actually matched to this opening brace. That is in this figure, the corresponding braces I am referring to are this and this, like the outer loop, right? Whereas here the problem is, I mean, we have, let me use a different color. So yeah, so in this scenario, this and this are kind of matched braces, but then there is no one to match this last closing brace. So it's an invalid structure. So if you write a C program where you have such a sequence of opening and closing braces, for sure you will get a compiler error, because this cannot happen actually, right? So if I ignore the rest of the programs and just focus on what are the valid sequence of opening and closing braces you are allowed to have, so we can abstract this problem, and this problem is called the problem of balanced parenthesis. So there are basically two restrictions. So like there are two things that you need to follow in this. So number one is, okay, so I'll just introduce one small notation. So I'll use this hash of opening to count the number of opening braces. This just means number of opening braces, and similarly hash of closing brace. It just is a shorthand for number of closing braces, right? So there are two things. So if you have such a sequence of opening and closing braces, the number one property you want is this total number of, like, over the entire sequence, the number of opening braces should be equal to number of closing braces. So which you see is satisfied here, right? In this first example, because there are three. So what is the count? There are three opening braces, there are three closing braces. Okay, but that by itself is not enough. Why? Because, okay, in this sequence, of course, this condition itself is violated because you have one opening brace and two closing braces. But suppose I just modify it a bit and I consider this sequence. Now see here, this is also an invalid sequence, right? You cannot have an opening brace first followed by, a closing brace followed by an opening brace. But here the first condition is actually not false, because the total number of opening braces is 2, number of closing braces is also 2. So this is not enough to characterize this, what is a valid sequence. So you need one more characterization, that is over every prefix of the sequence, so what is a prefix? Prefix means sequence. If I just choose, if I choose, let's say, only the first three symbols from here. So this is a prefix. This is a prefix of length 3. Or I can choose all these 4 together. This is a prefix of length 4. Right. Similarly, here I can choose, this is a prefix of length 3. Right. Okay. So we know that over the entire sequence we must have number of opening is equal to number of closing, and over every prefix of the sequence we must have number of opening greater than equal to number of closing braces. Now see how this helps. So let's consider the first one. This is a valid sequence, right? So here, let's consider every possible prefix. So if I look at a prefix of length 1, here the count of opening braces is 1, count of closing braces is 0. That is only up to, I am counting only up to the first position. I am ignoring the remaining remaining braces. So if I look at the subsequence only up to position 1, count of opening braces is 1, count of closing braces is 0. So this satisfies condition 2, right? Let's consider the prefix of length 2. So here count of opening braces 2, count of closing braces 0. So once again it satisfies this condition, right? What about prefix of length 3? So once again count of opening is 2, count of closing is 1. So 2 greater than 1 is satisfied. Take a prefix of length 4, it's 2 and 2. So it's, I mean, it's okay even if they're equal. So it just needs to be greater than or equal to. It cannot be strictly less than. Then again, take prefix of length 5. So number of opening is 3, number of closing is 2. So still it follows. And finally, the entire string is like a non-trivial prefix of itself. So here again, it's equal. Right. Now, so here for this sequence of opening and closing braces, both the conditions are satisfied, and this is a valid such sequence. Now consider the second one. So we have already seen the first condition is actually satisfied. That is, over the entire sequence we have number of opening and closing both equal to 2. But now let's consider the prefixes. So for prefix of length 1, the condition is satisfied. Number of opening is 1, number of closing is 0. So condition 2 is satisfied. Take a prefix of length 2, still the condition 2 is satisfied because they are equal, both are 1 1. But now comes the catch. Take the prefix of length 3 here. Once you have this prefix of length 3, you see here number of opening braces is 1, but the number of closing braces in this prefix is 2. So number of opening is strictly less than number of closing braces. So the condition 2 has failed, because note that it has to hold for every prefix of the sequence. Right. So for this prefix of length 3, the condition 2 has failed, and hence like this string is not a valid like string with balanced parenthesis. It's not balanced parenthesis. Okay. So yeah, so that's basically the problem definition. There is another interesting way of looking at it actually, kind of in a graphical manner. So Yeah, so you can think of it in this way, that if you look at the graph of the difference between opening and closing braces. So what I have plotted here, this, like, the x-axis is like for each prefix of the I mean, what's the difference in the count of opening and closing braces after considering each prefix of each length, and the y-axis plots the difference between hash opening minus hash closing. So the idea is that in order for a sequence to be a balanced parenthesis to satisfy these conditions, the way of graphically looking at these conditions is this condition 1 and 2, that this function of the difference between opening and closing braces should start at 0, it should end at 0. So ending at 0 means, like, at the end of the sequence I have equal number, that is, the difference is 0. On the other hand, because every prefix must have, like, uh, I mean, number of opening parentheses strictly greater than equal to number of closing parentheses. So this line must always, it can never go below the x-axis. It might touch the x-axis at some other place also, like here, in the first example, if you recall, if I took the prefix of length 4, at the end of prefix of length 4, but it can never go negative. That's why I said it cannot go below the x-axis. It can touch the x-axis at various points other than the last at the end, but it can never go below the x-axis. So that is one way of graphically thinking about what conditions this needs to satisfy. Okay, so I hope the problem is clear. What is this problem of balanced parenthesis? Now I'll give you a nice method to solve this using this stack. So hopefully that will build some intuition regarding, like, why stacks are useful. So this is one of the most sort of fundamental problems that you usually solve using a stack. So I'll just shift to a new board. Let me just copy this part for continuity. Okay, so yeah, let's try to see how what would be a nice solution. Okay, so remember we are going to solve it using a stack. So let me draw the stack. We will use actually these two examples only to see, like, how it works with the stack, like the two cases of the algorithm, when it will sort of say that yes, this is a valid string of balanced parentheses, and when it will say no, this is not a valid string of balanced parentheses. So let's draw the stack. So this is my stack. Okay. So let's work with this first example. So I'll show you with an example, and then I'll give you the general algorithm. That usually works better. So how you do it is, Okay, I'm just writing down the input once again. So this is the input to the algorithm. Now, initially you start with pointing to the first uh, symbol, first symbol in the sequence. That is this one. Now, when this symbol is an opening brace, what you do is you basically push it into the stack. So remember this term push means adding it to the top of the stack. So initially the stack was empty to begin with. So top and bottom are equal, like initially. So initially since it's empty, like the bottommost position is the current top. So I add this here, and then I am going to basically move my arrow. So I am now going to take a look at the next symbol in the sequence. Okay. Now you have another opening brace. So once again I follow this, I do the same thing, that is I push this opening brace into the stack, and I advance the arrow further and look at the next symbol in the input. Okay, now we have a closing parenthesis. So whenever you see a closing parenthesis, what you have to do is you go to the stack, and if you see at this point that the stack is empty, then you are going to return an error. That is, this is an invalid sequence. But here we see that on top of the stack we have an opening parenthesis. So what we do is we simply pop it. So I am like showing it with a cross. That is, I now popped out this element. So now the stack has only a single opening parenthesis. So I pop this the opening parenthesis on top, and then I again move my arrow one step forward to the next symbol in the input. And once again I have another closing parenthesis. So it's the same idea. So I'll pop the opening parenthesis at the top of the stack. So once again, if I had found the stack empty at this point, I would have returned an error, that is this sequence is invalid. But here I do find an opening parenthesis on the top of the stack, so I pop it. Okay. And once again, I move my arrow forward. Let's process the next symbol. So now I have another opening parenthesis. So now remember I had popped the previous opening brace. Now I just pop in this new one. So the one I just popped out, that was the one which was corresponding to the first symbol in the input. And the one which I have just pushed in, this corresponds to the fifth symbol in the input. Okay. Yeah, so I push this in and I shift my arrow to the last symbol. And this is a closing parenthesis. So I again pop the opening parenthesis found on the top of the stack. And now when I have finished processing my input, so my arrow is at the last position and I have processed it. Now I check back on the stack and see if at the end of all these operations, the stack is back to being empty. And if that is the case, since here at the end of all this the stack is empty, I say that, okay, I accept the string, that is I return that it's a valid sequence of balanced parentheses, which is correct, right, as per the conditions given. Now let's also try run it on the other sequence, that is the invalid one, and let's see what happens here. So let's run it on the other case. Of course, here the input is different. Here I am going for the input. Opening, closing, closing, opening. And once again, I start with the arrow pointing at the first symbol. So again, it's a similar way. So this time I'll go through it a bit faster. But so initially I see an open parenthesis. So I just push it in. Then I next, and then I advance my arrow. Now it's a closing parenthesis. So immediately I pop this opening parenthesis from the top of the stack. Okay, and now something interesting happens. So now once I move the arrow, now I have seen another closing parenthesis. But when I go back and look at the stack, at this point, there is no opening parenthesis now on the stack which I can pop. So basically the stack is empty right now. So once I come to this condition that I am seeing a closing parenthesis, but on the stack there is no corresponding opening parenthesis to pop off, and the stack is actually empty. So this here I realize that okay, this must be an invalid sequence. If you think about it, what this means in terms of the conditions is that at this point I suddenly discovered that I have, I mean, up to this point, if I consider the prefix of the string, I have basically discovered that I have found more closing parentheses so far than opening parentheses. So it's violating condition 2, right? And maybe just one more case. So let me just give one more example. So here the input I am considering is this one. So I am opening, closing, and then an extra opening one. Okay, so here how does this work? So initially I have my opening parenthesis. So I push it in. Advance the pointer. Now I have a closing parenthesis. So I pop off this opening parenthesis. And advance the pointer. Now I have another opening parenthesis. So in the stack, I push in this one. But now I have reached the end of the string. I have completely scanned the sequence of parentheses, but I find that at the end of it, the stack is not empty. That is, I have some additional opening braces lying on the stack. Just compare it with this scenario where by the time I reach the end of the input sequence, the stack had again emptied out. But here that's not the case. Here the stack still contains an opening parenthesis. And what this means is that at the end of the sequence, you have ended up with more number of opening parentheses than closing parentheses. So condition 1 is violated, right? So this again, in this scenario, it's going to kind of say that no, this is not a valid balance parenthesis string, right? So basically there are, so this was a scenario where my algorithm sort of returned yes, this is the valence parenthesis. This is a scenario where it said that no, it's not, because at some point, like at some prefix, uh, I have encountered more number of closing parentheses than opening. And here is a scenario where condition 2 was always okay, but at the end of the string, I have ended up having more number of opening parentheses than closing. So condition 1 has been violated, which basically, I mean, how do I detect this? That by the end of the scanning process, at the end of the scanning process, the stack is not yet empty. So that means there were more opening than closing. So this is again a scenario where the algorithm says, no, this is not a valid sequence of balanced parentheses. Okay. So I hope this problem is clear and you have some intuition about how a stack can be useful. Right. So now I think I can pause a couple of minutes for questions. So now I'll take you to the idea of what are these infix, prefix, and postfix expressions. So yeah, I'll just pause for a minute or two. Have any questions from the previous part? Just let me know.
So students, please ask question to sir. Any confusion or any questions, please ask.
Yes, Pritam. Pritam, I have one question, small question. Pritam,
Yes, go ahead.
according to your example, you have shown that you have used only one type of parenthesis, like second bracket. But if I use
Yes.
first bracket and third bracket, so in between first bracket, third bracket, and second bracket, is there any preference when we are going to implement comparison
No.
concept in stack
So
operation?
if you have no, actually that's a good question. I can maybe show one quick example. So instead of being a single type of bracket, so let's say there's a mixture. So
Okay.
uh, yeah, let me actually do an example of that type since you
Okay, sure,
mentioned it.
sure.
So I am considering a slightly more complicated version of the problem where you can have a different type of parenthesis. Like for example, your input could be, let me clear the stack. Uh, so let's say you have this, then in between you have a this parenthesis, like first bracket instead of brace, and at the end again, let's say you have this, the third bracket. So you have a mixture of different types. Now when this happens, it's you need a slight modification of the algorithm. So let's see this. So initially you see a opening brace that you push it in, then again you see another opening brace, you push it in, and like after pushing in these two, my arrow has reached the first bracket. Now it's the same idea. Basically, whenever you see any type of opening parenthesis, you just push it in. So in this part there's no change. But now when you see a closing parenthesis, like here you encounter your first closing parenthesis, you have got to be a little more careful. So at this point, you need to see whether the top of the stack has a opening parenthesis of the same kind. Like here you have a closing first bracket. So on the tag only if it's opening first bracket, you are otherwise at this point the closing second. Then at this point you would have thrown an error because you have the it matches, and it's again the same idea. We are going to just pop this from the stack. Here you find a closing parenthesis of second bracket. Then you go to the next position, again closing brace, you pop the, I moved here, now here. So I've point, the stack has again emptied out. Now once again, you have a opening brace, so push it in. Then you have an opening third bracket. So I push that in as well. So, and now I've reached the closing third bracket. So once again, it checks the top of stack. So it's a opening third bracket. So it's a opening bracket of the corresponding type. So in this case, there is no error thrown. I can just pop it off. And then it goes to the end. So it's a closing brace, that is second bracket. So there's a corresponding opening second bracket. And finally, I reached the end. I've processed till the end, and I find the stack is empty. So this is accepted, like this is a yes instance. Okay. So as I said, the main thing you have to keep in mind is when you see an opening parenthesis of any type, you can blindly just push it in. But when you see a closing parenthesis, you have to check it carefully against the top of the stack. Like here, it's not enough to just see whether the stack is empty or not. Even if it is non-empty, the top element on the stack has to match the type of the bracket. That is, that opening bracket has to be of the same type. Only then you can, it's not a valid balance parenthesis. Okay. Yeah. So moving on then to this infix, prefix, and postfix expressions. Okay, so firstly, let's talk about how we as humans typically write our mathematical expressions. So usually if you write a mathematical expression, it will be of the form, let's say, something like this: 3 plus 4 into 5 divided by 6. Right. Now note here, this expression, the form is like you basically have an operand, that is some value, followed by an operator. Like in this case, the first operator is plus, then again some operand like 4, then again some operator, let's say the second operator is star, then again some value, and then again some operator, and again a value. So basically every operand, like, so this is known as infix expression, by the way. So here what happens is no two operators can come side by side, right? I mean, so I cannot write something like 3 plus plus 4. I mean, we know this, right? I mean, in general, if we write an expression like this, it makes no sense. Or even something like 3 plus star 4 makes no sense. So no two operators usually can come side by side. So they each need to be separated by at least one some value in between. Okay. Now, what is the problem with this? Like, this is what we humans typically use, right? But for a computer, this poses some problems. Why? So first thing is, okay, so as a human, how will you sort of evaluate this expression? So in the first round, so you will do it in different steps, right? Initially, you know that by so because there are precedences involved. Like, you know that by this BODMAS and all, you should not do the addition first, right? I mean, you are not going to first, like, if I convert this into 7 into 5 by 6, this is not correct, right? I mean, you are not supposed to add first. You are supposed to do the multiplication. So you will first scan the input. You will locate which is the operation which has the highest precedence. So you will do the 4 into 5 here. You will get to 20. Then again you will do another scan, and you will find that, okay, still you are not allowed to do the plus. You cannot write this as 23 by 6, right? That is again wrong. So you have to write it as 3 plus. Okay, let me change this a bit just for easier computation. So 3 plus 20 by 10, which is 2. And finally 5. Right. Now just think of it in terms of an algorithm. So for you, I mean, for this kind of small expressions, it's relatively easy to quickly spot. It has to do one complete scan, locate the operator with the highest precedence, then sort of compute that part, then again like basically get a slightly reduced expression like this, then again scan the whole thing, locate where the operator with the highest precedence lies, then again reduce that part, so that you get this reduced sub expression 3 plus 2, and then finally it does it. And also if you want to like change the precedence of operators in certain cases, like if you intentionally want to add first, so in order to specify that, you need to put between parentheses has the highest precedence. So here you are actually going to do 12 into 5 and then convert to 60. But again, for a computer, it's unnecessary because you are having to introduce these extra symbols, like the open and closing parentheses, to point out that in this case I should do the plus first. Now let's see how postfix expressions work, and you will see immediately why there will be no need for uh, parentheses there. So let me actually show you the corresponding postfix expressions for these two for these two infix expressions, and then I'll explain. So actually postfix, as the name suggests, postfix means you have the operands first followed by the operator. Like here you cannot have two or more operators side by side, whereas in postfix you can have operators side by side. So let me show you the postfix expression for this 3 plus 4 into 5 divided by 10. So for this one, the postfix expression will be so this is how it looks like. Now I mean, for us humans, it's not immediately obvious how we should evaluate this. So I'll come to that. Let me also write for the other one. So this is the corresponding postfix expression for 3 plus 4 within bracket into 5. So note here that you have the two operands 3 and 4 together, then the operator you have to apply on them, and then basically it's like one sub expression 3 4 plus, then one operand and followed by an operator. So it's always like each operator has to be preceded by either two operands or one sub expression and one operand, or two sub expressions. Okay. So how do we evaluate this? So see, for a computer, this is actually quite easy to do. So let me first show you how postfix expressions are evaluated, and then I'll talk of how we can algorithmically convert from infix to postfix. So let us take this particular expression. Okay, so we take the help of a stack to evaluate a postfix expression. So we start with an arrow pointing towards the first symbol in the expression, and we create a stack. So how does a stack look like? So typically we imagine stacks as like things which grow from the bottom towards the top, but here for convenience, I mean, instead of drawing this structure each time, I'll just like write the stack from left to right. So basically, I mean, when I write it left to right, it just means that the leftmost symbol is the bottom element of the stack and the rightmost symbol is the top element. So I mean, you just think of, I'm just flipping the stack like 90 degrees. Okay. So it's just to save some time instead of having to draw this out every time. So I'll do two things. So one is after each step I'll shift the arrow and I will write the new contents of stack. Okay. So initially stack is empty and you have the arrow pointing towards the beginning. Now when the arrow is pointing towards an operand, like here 3 is an operand, like not an operator. So you just push this into the stack and you move on to the next symbol in the input. So once again, it's an operand. So you push this into the stack, move ahead, scan, move the scan to the next symbol. So once again operand, you push it in and you move the arrow. Now you have come to an operator at finally. Okay, so now that you have come to an operator, so you never push an operator onto the stack. What you do is from the top of the stack, you pop twice. So you pop the top two elements from the stack. So I'll pop 5 and I'll pop 4. So basically now on these two operands that I've just popped from the stack, I will apply the operator. So that means what? I am looking at the operator star, that is multiplication. So I pop 4 and 5 and I do multiplication on 4 and 5. And the value that you get, that is 20. So that new value now I am going to push into the stack. Now see what has happened. So the stack, before I process this operator, the stack consisted of 3 operands, 3, 4, 5. Now after processing this operator, I have actually multiplied the top two elements on the top of the stack 4 and 5, and the result I got, that I have pushed onto the stack. So now my stack consists, at the end of this step, when I finally shift this arrow to 1, or rather 10, now this contains two elements, 3 and 20. 4 and 5 are gone basically. Okay. Now 10 is again an operand, so I'm going to push 10 in, and I'm going to move the arrow forward. And now again I've encountered an operator, that is division. So at this point, once again, the idea is you pop the top two elements from the stack, in this case 20 and 10. You apply your operator, that is division, on these two values, that is you do 20 by 10, and the new result that you get, that is 2, you push back onto the stack. So now, after processing the division operator, the stack consists of, so before this operation, the stack had 3, 20 and 10. Now after processing, the stack has 3 and 2. And once again, I will be popping the two operands on top of the stack, that is 2 and 3. And whatever is the final result, so temporarily I just write this 5 back into stack, but once I see that there is now nowhere further to go, that is I have reached the end of the input, so whatever value is on the top of the stack, I return it as my, but the important thing is it does so in a single pass on the input. See, here I just did one linear scan from 3 to the end, and that actually gave me the value just by using this data structure, the stack, as a helper call. I needed to do multiple passes. On one pass, I had to read the entire string and see where I have the star appearing, which is the highest precedence operator. So then I reduced, then I applied that, then I again did a fresh scan, and then I got the division, and then, so basically I needed 3 passes here on the infix expression to evaluate it effectively. But here on a postfix expression, with the help of this stack, I am able to evaluate the entire thing on a single left to right pass, right? So that is a huge advantage. In fact, yeah, so that is one of the advantages, right? So it's much more efficient for a machine to do. You don't really need parentheses because, I mean, so see, I mean, let's understand the difference here. If just a minute. So let us just to compare. Let us have the expression like without the parenthesis. That is 3 plus 4 into 5. Okay. So here, how it should be evaluated? So I should have 3 plus 20. That is 23. Now, let's so for the with the parenthesis, the postfix expression was T4 plus 5 star. And if you don't have the parenthesis, then you can write it as follows. You can write 345 star plus. So this is the corresponding postfix expression. So if you again apply the stack algorithm to evaluate, you will see this both will evaluate correctly. So because here what you will do is after 3 and 4 you encounter the plus, right? So you basically apply it on 3 and 4. So you have, so let me quickly show you how the stack grows for both of these expressions. So first one, 3, 4 plus 5 star. Yeah, so start with my input pointing here, and yeah. So how does the stack grow? So initially you see two operands, 3 and 4. So you push them in one after another, and then when you encounter your first operator plus, so you are going to pop both of 3 and 4 and apply plus on them, so you get a 7, and you add the 7 to the top of the stack, push the 7 onto the stack. Now next one is again an operand 5, so you push it in, and then you hit the end symbol, which is star. Right, so you apply star on sorry, click here. Yeah, so I apply the star on 7 and 5. I pop those. 7 and 5 are popped, and instead I push in 35. And now that I have reached the end of the string, I know that 35 is going to be my final answer. Okay. Now, quick comparison the version without parentheses. So I claim that its corresponding postfix is 3, 4, 5, 5 star plus. So this is how it looks like, and initialize with pointer pointing at 3, and the stack is initially empty, but you push in 3, 4, and 5 one after another because they are all operands. So as long as you don't see an operator, you are going to just keep pushing the new operands into the stack. So 3, 4, and 5 have been pushed. Then you finally see the star. So what is the typical rule? At this point, you pop 5, you pop 4. And you apply star on them. So you have 4 into 5, 20. So you already had 3 in the stack and you push in this 20 here. And then as soon as you move one more step, you have again hit another operator. Now the two elements of the at the top of the stack are this 20 and 3. So you apply the plus operator on these two operands. And you get 23, which is the final answer. Right. So is it clear how postfix expression helps for the computer to evaluate arithmetic expressions quicker? Okay. So now that you have some motivation behind how, like why I should want to convert to postfix, let's go ahead and see the actual conversion algorithm. So once again, it uses stack, right? And we will actually start with this example itself. This, let's say 3 plus 4 into 5 by 10. So this is without parentheses. So first let us understand the logic without parentheses, and then we'll also do one more example where we have an arithmetic infix expression with parentheses. Okay. So I am moving on. I'm just opening a new board. Right. Yeah. So this is your expression. So once again, I'll just use I'll draw the stack like left to right, but basically remember that left means it's the bottom of the stack, right means it's the top of the stack. So that's why all the pushing and popping, everything is happening from the right end, because that is like equivalent to the top. Okay. So initially stack is empty. Okay. So I have two things going on here. One is how the stack looks after every point, and how the output expression looks. That is the so output will ultimately give me the postfix expression, right? So initially, I mean, with my uh, just a minute. Yeah. So with my arrow pointing at the beginning of the input. So initially, I have the stack is empty, output is also empty. So as I scan from left to right, both of these will change at every step. So initially, what I am pointing at, it's an operand. Now, once you have an operand in your output, you are supposed to just return it directly. That is, you don't. I mean, if it's an operand, it doesn't need to go into the stack. You can just directly add it to the output. So you add 3 here and you move on. Now you have a plus, right? So the moment you have an operator, so there are two things that happen. One is, this is a simple case where you have an operator and the stack is empty. If the stack is empty, you just push it onto the stack. So after this point, you just push the plus onto the stack and again advance your pointer. So it goes to 4. Now once again, it's an operand. So you sort of directly send 4 to the output. Okay, now something interesting happens. Now I encounter another operator, star, and now the stack is not empty. So this is crucial. So I've got another operator, but the uh, yeah, now the stack is not empty. The stack already contains another operator which is plus. Now when this happens, you need to actually compare the precedence of plus with star. At this point, if since star is actually a higher precedence, a strictly greater precedence than plus, so that's why star gets to push itself into the stack, and you advance. So remember, this pushing happens only when the new operator you have encountered, like where your arrow currently pointing to, that operator has strictly higher precedence than what was its other uh, other operators in below it in the queue, in the stack, right? Now there's this another operand 5. So I add it to the stack, and there's a division. Now division and multiplication are actually same preference typically, right? They are both plus and minus are same level of precedence, and division and multiplication are considered to be same level of dividends. Here, as I said, I push it in only when the new operator is strictly greater in precedence than the current one on top of stack. Now here that is not the case, right? So when you see that the current top of stack operator is less than or equal to in privilege, sorry, rather greater than or even equal to in privilege to your current operator your arrow is pointing out, you are going to remove all the operands from top that have greater precedence. So here it's only one, only star is there. Then when you go back to plus, it's actually lower precedence than division. But in general, like if there are 2, 3, or whatever number of such operators on the top of the stack, which are not strictly, which are actually strictly, sorry, less than or equal to in preference to is the operator that your arrow is pointing at. So in that case, you pop it from the stack and send it to the output. So here something interesting is happening. I'm actually popping the star from the stack, and instead I'm sending it to the output. Okay, and now that I have actually popped all the I mean in this case only one, but in general I popped a sequence of a string of operators from the top of the stack which were all having precedence greater than or equal to b, right? And now I am free to push in the dollar here, sorry, the division here. Okay, I push in the division and then I move ahead. And I encounter another operand which is 10. So as I said, whenever you encounter an operand, send it directly to the output. You don't even need to go via stack or anything. Okay, now you have reached the end of the input, but in order to complete the postfix expression, you need to look at what is still lying in the stack. So in this case, you first have a division, So you just pop from the stack in reverse order. Uh, so you are going to add the division symbol first, and then finally you are going to add the plus symbol. And this is the corresponding postfix expression I got algorithmically. We can just quickly go back to the last page and check that this was indeed what I had given. Yeah, this one. Okay. So this was how to. So this was a simple expression because here you did not have parentheses or anything, just operators and operands. Now let us do one more slightly more complicated example where you also have some parentheses. Okay, so let me choose some example. Okay, so here's my yeah. So we have actually quite a few sets of parentheses here. So we have, this is just to show you how to deal with the parentheses in there. And then once I'm done with this example, I will write down the sort of actual algorithm in pseudocode. And you will see how things come together. So I'm starting with my arrow pointed at the right at the opening bracket. So I don't know what the input will be. I'm clearing it out now. What the output will be, and here also. So initially it's an open parenthesis. So whenever you see an open parenthesis, the rule is simply blindly push it onto the stack and advance. Then it's an operand 30. So once again, just bear with me. So 30 I just send directly to the input. Now I have a plus. Now currently at the top of the stack there is only a parenthesis, but there is no other symbol to compare it with. So if I see that the top of stack currently is a open parenthesis, then I simply add the operator to the stack. And after that we have an operand 23. So I just directly send it to the input. Okay, so now we have come to this point. So I've added the plus to the stack. I've sent 23 to the output, and now I've come to a closing parenthesis. Now, what happens when you encounter a closing parenthesis? So, whenever you encounter a closing parenthesis, you need to pop the stack all the way up to till you find one opening parenthesis. So, for example, I mean, in this case, what will happen is I'll be and when I remove this from the stack, I'll be adding it to the output. So there are two things going on here. One is this plus is popped from stack, pushed into output, and then you can, once you have actually out popped all the operators up to the and encountered your first opening parenthesis starting from the top. So you can just pop it and discard it. So now once again the stack becomes empty. Okay, maybe I should, doing it like this, I should just write down and then scratch out like I was doing. So yeah, so we have got 30, 23 plus, and I process the opening parenthesis. Okay, now we have encountered star, which is an operator. Now the question is, so when you encounter an operator and either the stack is empty, as is happening in this case, or the previous element is an open parenthesis, then you just blindly uh, put it into the stack. So in this case, like this, I'm going to put opening parenthesis and and sorry, first the star and then the opening parenthesis into your tag. So I pushed in the star and the opening parenthesis, and now there is 43. So that being an opener, I'm just going to push it in. Okay, now there is a negative sign. So, so once again, I mean, if you are trying to decide whether I should pop this into the stack or not, so here the decision is relatively easy for you, because I mean, whenever the top of the element is an opening parenthesis, or the stack or the stack itself is empty, then you don't need to really think much else, and you can just blindly push the operator onto the stack. So I pushed the minus here, then there was another operand 21. So that also I send directly to output, and now I've come to this point, the closing parenthesis. Now if you recall, whenever I see a closing parenthesis, you have to pop all the symbols before the first closing parenthesis from the right, that is the first one from the top. You have to pop everything up till until you encounter the opening parenthesis on the top of the stack. So here there is only uh, one operator in between, that is minus, and you are going to remove both this operator minus as well as this opening bracket. So see, everything I am copying from the stack. If it's an operator, I am adding it to my output. That is the final postfix expression. But if it's any kind of parenthesis, I am never going to include it in my postfix because I never need parenthesis in my postfix. I'm setting it up in such a way that you will see it will evaluate to what I want. Okay, and then okay, now something interesting happens. So now I have got I process the closing parenthesis and I've come to a division operator. Now, currently at this point, what does the stack have when you have reached this point? So after popping whatever needed to be popped, you just have star on the stack, and the new operator that is being pointed to by the pointer currently, that is division. Now division and star have equal precedence. None is greater than the other. Okay, and if you recall, I said that I mean, unless those special cases where it's the stack is empty or this or there is an opening bracket on the top of the stack. Apart from that, in all other cases, you need to compare the precedence of the incoming the incoming operator where I am currently pointing to with the operator on the top of the stack. So here the top of the stack has star, that is multiplication, and the current operator I am looking at is division. So it is not strictly greater in terms of precedence. If it was strictly greater in terms of precedence, I would have pushed it in. But here, because it's not strictly greater, I do the reverse. I actually pop everything in the stack which is from the top. I go all the way down till I encounter at least some operator which is equal or higher in precedence. But here there is only start to output, and after that the stack is anyway empty. So star is actually moved from the stack to the output, and then you actually add the division operator here. Okay, and then again you have an opening parenthesis, so you just push it in blindly, and then you so I move my arrow over these two symbols. I've gone to 84. So 84 being an operand, quite simple actually. Just push it in. Then you have a plus. So whenever you have on top of stack an opening parenthesis, you are always going to push the operator encounter. So push the plus here. And then you have 7. So 7 being an operand, once again, push it in. And now, finally, I have reached the end of the input and I have reached this closing parenthesis. So what was the rule for closing parenthesis? You have to basically pop all the operators up to when you encounter the opening parenthesis. So in this case, there is only plus to pop. And then this opening parenthesis I also pop, but I don't send it to output, I just discard it. So what I have done is I have popped the plus, then I have popped the opening parenthesis, but the plus I send to the output, the parenthesis I never send to the output, because as I said earlier also, postfix expression does not require the parenthesization. It actually captures that information in the sequence, in the way it sort of converts. And then finally, I've reached the end of input, but there is one operator on the top of the stack, that is the division. And I just again pop it from the stack, send it to the input. So this is how the infix to postfix expression works. So I'll leave it as a small exercise for you. If you guys like evaluate in a normal way, that is an infix, the value you will get, and if you use the algorithm for evaluating postfix using stacks, you will see that this is correct, that it's exactly uh, what I wanted, what should be the value of this expression. Okay. So finally, just one word to finish off. So I did not really talk about prefix expressions, so I'll quickly introduce it. Uh, so as you might have guessed, like infix means you have all operators in between two operands, right? So you cannot have two operators side by side. It has to be cushioned on either side by operand. Postfix means you should have like operands followed by the operator. Right, like here you have 3023, two operands followed by the operator plus, and 4321, two operands followed by minus. Right. Then these two sub expressions, that is 3023 plus this entire sub expression, and 4321 minus this entire sub expression, these two sub expressions followed by star. So as I said, in postfix you always have either like two objects which can be either sub expression or operand followed by an operator. Now in prefix, it's just the other way around. You have the operator first, followed by a couple of objects which can be, you know, operand or sub expression. So, for example, quickly let me write down the prefix expression for, let's say, 3 plus 4 into 5 by 10. So 3 plus 4 into 5 by 10. This, if you convert to prefix, it will look like this is how it will look like. So you see, you have star followed by two operands, operator followed by two operands. So this is one sub expression. So you have the division operator followed by this one sub expression and one operand, and you have the plus followed by one operand and this entire sub expression. Right. So this is how prefix works. So once again, the advantages, prefix can be very easily evaluated using stacks. It's very similar to how the postfix works. And also for the conversion part, actually, if you know how to convert from infix to postfix, then prefix is not so hard. I'll just quickly tell you how to do it. In fact, it uses the conversion of infix to postfix as a sort of black box, as a submodule rather. So here's the 3 steps you need to follow. So first thing, what you do is you reverse the infix expression. So let's do this with the help of an example. So let's say you want to convert a plus b star c into the corresponding prefix expression. So first step is you have to reverse the infix expression. So it becomes c star b plus a. Just reversed it. Okay. Once you reverse it, you obtain the postfix expression of the reverse of the infix. That is, so you have to obtain the postfix expression for this reversed infix. That is cb star a plus, which will be, so what will be the postfix expression for this? So let's do this. So you are trying to convert a plus b star c. So the first step you do is you reverse it. So you get c star b plus a. Then you obtain the postfix of this c star b plus a. So what will be the postfix of this? So you will have cb star a plus. Okay. And finally, this postfix that you got, you reverse the postfix expression. You just flip it back. So you get plus a star b c. So this is basically a reverse step. Here you do a convert to postfix, and here again you do a reverse step. Right. And that is how you go from infix to prefix. So this step you already know how to go from the one infix to the corresponding postfix. So basically, as I said, I am using this as an intermediate step. So you reverse the original infix, you compute the postfix corresponding to the reversed infix, and then the postfix expression that you get, you reverse that, and this actually gives you the prefix expression. Okay. And how do you, just one last thing, how do you evaluate prefix expressions? It's very similar to what you do with how you do for postfix. So let's say this expression itself, plus a star bc. So how will you evaluate it? So once again, you need a stack to evaluate the prefix expression. So plus a star bc. So once again, I will have the stack.
Hello, Pritam.
Yeah, yeah. This
My
is
voice
the
is
last.
my.
Yes.
Hello.
I'm saying this is the last topic. I'll wrap up in 5 minutes.
Actually, I have a question. I have a question regarding this topic.
Okay. Huh.
Okay. After you complete, then I will ask. Okay, right.
Yes, that is better. Just let me show them this. Okay, so this is the stack, and as usual, I start with a pointer to the beginning of the expression. So actually, the interesting thing is you start with the pointer at the end in this case. For evaluating prefix, start with your pointer, very similar to postfix. So whenever you find that you are reading an operand, you simply push that operand onto the stack. So you push C onto the stack and you move your arrow to the left one position. Once again, you are reading an operand, so you just push this onto the stack and move your arrow, move the pointer. Now, basically, pop the top two operands from the stack. In this case, I pop B and C, and I push in the product of B and C. That is, you apply the operator on these two operands and push in the result here. So I push in B into C into the stack. Like whatever is the value of B into C. Like I evaluate B into C and I push that in. And then move one step to the right, one step to the left. So it's another operand. So I again push step to the left. So I encountered an operator. So once again I have to pop the top two operands from the stack. So I pop A, I pop B star C, and since now I've reached the end of it, like whatever is the I basically apply plus on these two things, and so my final answer will be just what I get. Right. But except in the reverse order. Right. I mean, you just do the scan in the reverse order. Otherwise, the algorithm is exactly the same. Okay. All right. So I think that is all questions. Yeah. Any questions? Yeah, I'm basically done with my presentation part. So if you have any questions, then I'd like to address, or then we can wrap up.
So any questions from students? If there is any question, please ask. Also, I have posted the attendance link.
Yeah, if there are no questions, I guess we can wrap up. I can share the slides that I like the board work I did. You can
Okay,
share it with
sir. You can share
the
the slide,
students.
and also I will share the link as well after I upload in the YouTube. Okay, sir. And Shidata sir,
Sorry, your voice is getting distorted.
Hello, Pritam.
Yeah.
Actually, right now my mobile charge is only 18%. So in this consecution, in this prefix, in this in this consecution, my question is the precedence and the precedence or priority of both the operator like addition and subtraction are same, but from left to right direction, which is found first is executed first. Similarly, multiplication and division, both the operator.
Go ahead.
Multiplication division, both the operator precedence and priority are same from left to right, which is found first executed first. But when, my question is, when dollar sign, exponential sign, hash sign, everything is there, then how we can convert from left to right direction? That means in between dollar, hash or exponential, which is
no, if you have exponentiation, that you will give a clearly higher precedence than division and multiplication.
And hash and dollar, another two, hash and dollar.
What is hash and dollar?
Hash means hash input std.h. This hash sign, hash.
No, but that's not an arithmetic operator. I am just talking of evaluating the arithmetic expressions. I am only talking of like evaluating arithmetic expressions. So it should not have any operator which is, then it's just an invalid expression. I mean, you have to, if you add an operator, you have to define it. Like what does hash mean? Or I mean, I'm not talking of parsing an entire program. I am only talking of parsing and evaluating an arithmetic expression.
Okay.
So Siddhartha sir, please conclude the session.
Okay. Yeah. So just one comment in relation to what you said. So here, as you observed, because in my algorithm for converting to postfix, if you recall, what I was doing is whenever I encountered some operator with like if I found that the current operator is only if it's strictly greater than the in terms of precedence compared to the operator on top of the stack, only then I pushed it in. Otherwise I popped the operators from the top of the stack, like all the operators which were less than or equal to in terms of precedence before pushing it in. Now if I modify this slightly and I say that, so this led to, like my current algorithm, as you observed, it leads to right to left evaluation for operators of equal precedence. Like here I first evaluated the 4 into 5 and then the division. But if I slightly tweaked it, that is I said that even if it's greater than or equal to in terms of precedence, then I will push it in, then it will get reversed. Like for example, here I would have pushed in the division operator before popping the star. So in this case, how it would have worked? So let me just quickly show the alternate. Like this is typically right to left evaluation is what we want, right to left associativity for operators of equal precedence. But just in case you want the other way. This is left to right associativity, the way it's working. If I want right to left associativity, that is, I want the division to be executed first and then the star, then what we would have done is, so I'm just showing the alternative here. So up to this step, it's same. Just a minute. So you have pushed in 3, 4, 5 and plus and star here. Now at this step, instead of popping the star and adding it to output, you will instead push in the division, because now you are pushing in when it's greater than or equal to, instead of pushing in only when it's strictly greater. Right. And then the 10 to output, and then you will finally, because you have reached the end of input, you are going to pop one by one and add it to the end of the output. So this is how it will look. So this will be the modified postfix. So here what you can see what is happening is we are first doing 5 divided by 10, then 4 into the result of that, and then finally 3 plus the result of the sum expression. So just by tweaking, making that little tweak, you can make operators of equal precedence associate from right to left instead of the standard left to right association. Right. Okay. Yeah. So that's what I wanted to comment.
Okay, sir. So thank you very much for this wonderful session. And
Yeah. Thank you.
okay, so and maybe in the future, if we can arrange such kind of sessions,
Sure.
we will always request you to please give or deliver the lecture like this fashion.
Okay.
So that's all for today's students. So I have already given the attendance link. So please fill up that attendance link. And sir, I will send you the link.
For the recording.
Yeah,
Yeah.
yeah,
So remember to turn off the recording before logging out. Otherwise, it creates a
yeah, yeah, yeah.
problem.
Sure, sure, sure.
Like the
Yes.
recording keeps running.
Yeah, yeah,
Okay.
yeah.
Just reminding you. Okay. Thank. Yeah.
Thank you, sir.
Okay. Thank you. Thank you for the opportunity. Bye.